Okay, it is time to get started. It's 11:30. Just to, well, I was going to say, if anyone still has assignments to hand in, feel free to throw them on a pile either at the break or at the end of class. That's the ones. And again, if you've still got them to email to me, feel free to do that anytime before midnight. I'll be marking them tomorrow. So as long as I get them by the time I check my email tomorrow morning, it'll be fine. What was I going to say about anything else before I get started? Nothing I can think about. Oh, I'll talk a little bit more about the quiz that's happening on Tuesday at the end of class, once I know exactly what's going to be on it based on what we've actually covered. So, today is Thursday, May 29th. Here's the agenda for today's class. My goal today for today's class is to get through both section 6.2 as well as 6.5. I'm leaving some stuff out that's in section 6.2 in the text, in the hope of being able to get through it faster. So 6.2.3 is on my handout, but it is not being covered this course. So I've changed the handout that was online, but I didn't want to have to reprint these guys. So if when you get one of these, if you could go to 6.2.3 and just like cross it out, so you know that you don't need to worry about it, don't need to study it, don't need to try those problems, that would be great. If for whatever reason I end up being really behind schedule today as well, I may also cut 6.2.4. We'll see how I am when I get to the end of 6.2.2, how I'm doing. Again, if I'm only 5 or 10 minutes behind schedule, I won't, but if I'm like 15 or 20 minutes behind schedule, I'll cut 6.2.4 in order to make sure I get to 6.5 today. 6.5 is actually one of the shortest and sort of easiest sections in the entire course, which is great. So if you're one of these people who is having difficulty with 6.1 and 6.2, 6.1 was on areas that we talked about last class, how to sort of find areas in curves. 6.2 deals with finding volumes, and that's going to be a little bit more complicated than areas. I'm not going to give you sort of the hard volume problems, but there are sort of enough of them that come up that there might be some difficulties that arise. 6.5 is basically just sort of knowing a formula and being able to apply it. It's a lot simpler. And then again, as usual, I'll be doing group problems at the end. So, okay, that's recording, good. Okay, why do I not group problems yet? Oh yeah, there's no muddiest points for today. I got a couple cards last class, I guess for people on the left side of the classroom who are having difficulty seeing the board. I'm going to make sure I do not stand here as much as possible. I'm going to do my best to stand over here when I'm talking, because then I'm not blocking the board for anyone. I apologize that sometimes, I don't know why my habit is to move right whenever I'm not writing, but it means I'm blocking the board for all the people on the left side, on that side of the room. So I'm going to try to do my best to stand over here. If I am blocking the way, please feel free to say, Kellen, please move because you're blocking the way. And this is another reason I'm doing these recordings, is hopefully if there's something you missed when the class actually happened, go to YouTube, find that spot in the course. You should be able to see it from this side, if you can't see it from that side. So, I mean, I know it's not ideal to be looking up on the YouTube to be able to find the stuff that you missed, but it is definitely an option, because otherwise it's hard for me to, unerase stuff otherwise. So sorry, we're moving into section 6.2. So last class we talked about finding areas, right? We talked about how you find the area between two curves. And the idea was that we found the area by sort of imagining that we're cutting up the area into rectangles, finding a formula for the width of the rectangle, finding a formula for the height of the rectangle, taking that thing and turning it into an integral, right? The idea was if we had two curves like this, and we cut it into rectangles like this blue one, right? The width of this rectangle is going to be delta x. And let's say this top curve is f of x and the bottom curve is g of x. The height is f of xi star minus g of xi star, right? It's the y coordinate up at the top minus the y coordinate down at the bottom. So that means that we can approximate the area with a sum of f of xi star minus g of xi star times delta x, or we can evaluate it with an integral of f of x minus g of x dx. Right? So that's sort of one of the ideas we talked about last class. Actually, I am going to move this integral down to the next line, and then I can do the other side over there. F of x minus g of x gx. Right, so the idea is I sort of talked a little bit about how, I just handed them out. There might be at the back of the class with the extras. That's usually where they end up. Yeah, sorry. I should have, if I collected them back up here, there would have been extras up here, but yeah. And when you get the 6.2 handout, cross out section 6.2.3. We're not covering it. So, the key thing I'm going to mention about this is this process of being able to take, okay, how do we use a rectangle to approximate something, getting the formula for a rectangle and turning it into an integral formula for the volume is an important process. And will come up throughout chapter 6. The other thing I talked about is what happens when we have two curves like this, right? There's like this one is x equals one function of y. This one is x is a different function of y. So here, these are y as a function of x. Here, x is a function of y. In such a situation, we can approximate an area by dividing it up into horizontal strips rather than vertical strips. When we divide it into a horizontal strip, this distance, the height of the horizontal strip, is called delta y. The idea is what we're doing in this case, we've got some integral on the y-axis for cutting into pieces. And the length of each piece is called delta y. The width here is an x distance. It's the distance between the x-coordinate here and the x-coordinate here. And these two x-coordinates happen at the same y-coordinate. So this x-coordinate will be f of yi star. This at y-coordinate will be g of yi star. Right, yi star is saying which y-coordinate are we picking. This is saying we're taking the f at that y-coordinate minus the g of that y-coordinate. So the area is going to be approximately the sum of f at yi star minus g at yi star times delta y. And if we turn that into an integral, it becomes f of y minus g of y dy. So the idea is, by sort of visualizing what's happening with the rectangles, we can find a Riemann sum formula for the area, which we can turn into an integral. How do we turn a Riemann sum formula into an integral? Delta y becomes dy, yi star becomes y, the sum sign becomes an integral sign. So being able to sort of understand where these formulas come from, how to turn them into integrals, is sort of an important part of what's going on here. Again, this sum formula in front just says that we've got a bunch of these different rectangles and we're adding them all up. That's the idea. So anyways, so this is the approach I used last class to dealing with areas. In this class, I'm going to use a similar approach to deal with volumes. We're going to cut things up. We're going to take the volume on each of those pieces. We're going to put a sum symbol in front to add it together, and then we're going to turn that into an integral. That's the idea. Any questions about this process before I move on to the specific example of volumes? Okay. So, the first idea that's going to come up when we're talking about volumes is the idea of slicing. The idea of slicing is the idea of what actually happens when we take a solid object and we cut it up. The same way we sort of did here, we cut up areas. Here we cut up areas like this. Here we cut up areas like this. We can apply that same idea to solid objects and use that idea to find volumes. So here's an example of a solid that we could find the volume of. Here it's a solid with base on the triangle with those three vertices and with cross sections perpendicular to the x-axis being squares. I'll talk a little bit more about how to visualize these sorts of solids in a second. The key thing I'm going to talk about first, though, is how to sort of come up with, how to sort of visualize what's going on when we're doing volumes. How many people have taken calculus 2 before and remember how to do volumes by slicing? Anyone? See a couple? How many people have learned how to do this and have to completely forget it? How many people have never seen this sort of stuff before? I guess that's most of the class. Great. Yeah, I was going to say, anyone who's taken house, this probably didn't come up in high school calculus, for anyone who did high school calculus stuff. Again, I will stress that they're hard, if you can visualize what's going on in these problems should become a lot easier. I know I find these problems easy because I'm a visual person. A lot of people are not visual persons. If that's your big difficulty, I don't know a real good way to get around the visualizing process, but try to see if you can do your best at trying to actually visualize what's going on here. So the first thing to mention is when we talked about areas, we cut things up. When we cut things up, the things we got were rectangles, right? If we cut them up into strips like that, the strips look like these things that are called rectangles. When we cut up solid objects, the things that they're going to look like are these things that are called cylinders. Now, a cylinder is a sort of more general thing than what we usually talk about when we talk about cylinders. Usually when we say the word cylinder, we think of like a circle on the top, sides, and a circle on the bottom. It turns out that there's cylinders that are not circular. So it turns out that a rectangular prism is actually a cylinder. This is like a rectangular cylinder. You know, if we had a hexagon on top and a hexagon on the bottom, like this, that's a hexagonal cylinder. If we had this shape on the top and the same shape on the bottom, and I'm trying to see if I can draw it, you know, in a sort of vertical thing that looks like that, that's also a type of cylinder. So again, the normal types of cylinders are circular cylinders, but there are other types of cylinders that are out there. Rectangular cylinders, hexagonal cylinders, weird sort of curvy shaped cylinders. So every shape comes with its own type of cylinder, and there's a formula which we can always use to calculate the volume of one of these things. And the formula is this. If you want to calculate the volume of a cylinder, you measure the area of the two parallel faces. So here are the two parallel faces, the top and bottom. Here's the top and bottom. Here are the top and bottom. So measure the area of these guys, multiplied by the height of the cylinder. So we're measuring the area of either the top or the bottom, and we're multiplying by the height. And that gives you the volume of any one of those shapes. Again, if the cylinder was this way, if we had like let's say it was a parabola, and it would look like this, we measure this area and multiply by this distance. Again, height sometimes is a sideways distance. But the idea is you're always measuring, so if you have two faces that look the same, we're always measuring the area of these two guys and multiplying by the distance between them. Sorry, I put that H sideways because I was visualizing it sideways. There we go.
That wouldn't work for where height changes on an object, would it?
No. So if we had, I don't know. I'm bad at, okay, let me do a better drawing of this guy. So if we had something with a triangular base and a square side on this side, but then it looked like that, that's not a cylinder. Yeah. If it's got a triangle on the top and a triangle on the bottom, those two triangles are not the same shape, they're not the same size, and they're not parallel. Yeah. So this formula only works if you've got two sides which are parallel, and the rest of the sides are just sort of cut out from that. So the idea is that if we have this formula, that any solid whatsoever can be cut up into things that look like cylinders. Let's suppose, for example, we had a pyramid. Pyramids are sort of relatively easy examples to do. And we sliced it, right? If we sliced it, this way. One of those slices is going to be that red piece that I've highlighted there. It's going to look like this. That red piece there. Now, it's not quite a cylinder, right? It's not quite, because this top here is slightly smaller than the bottom, but it's pretty darn close to a cylinder. The idea is that's approximately the same thing as something with a square top or rectangular top and rectangular bottom with the same size. And so we can approximate the volume of this guy with a bunch of volumes of things that look like this, of slices which have the same area on the top and bottom. And again, these things that are called cylinders. So when we are trying to calculate the volume of this thing, we're going to use sort of the same process that we did when doing areas. We're going to first pick an axis along which to integrate. Here, I've done it by integrating along this blue axis that goes like that. This interval here along the blue axis is what I'm cutting up into pieces. That's what I'm slicing along. The axis you're integrating along is always the place you're slicing along. So here, I was integrating along this axis, which means I'm cutting slices like this. So here, I'm going to cut slices like this. Each one of those slices is going to look like this. It's going to be approximately a rectangular cylinder. To calculate the volume of this thing, we need to do two things. We need to measure this area. I'm going to call it A of xi star. The idea is you've got to pick a point between here and here at which to calculate the area, right? Do we calculate the area at the top end point? Do we calculate the area at the bottom end point? Do we calculate the area at the midpoint? Right, there's different possibilities for where we calculate the area. Do we calculate the area at the top of this thing? Do we calculate the area at the bottom of this thing? Do we calculate the area halfway between? Right, they're going to be slightly different areas. Pretty close, but slightly different. So that's xi star is telling you where do you calculate the area. Calculate the bottom, calculate the top, calculate in the middle. So the thing you've got to multiply is this distance. This distance is delta x. It's the length of each slice that we're taking, or the width of each slice that we're taking. It's the size of each of the pieces that we're cutting this integral into, right? We're cutting this integral into a bunch of different pieces, and we're calculating the volume of each piece. So the volume of each guy, of each cylinder, is going to be approximately A of x I star times delta x. It's going to be approximately the volume of each cylinder, right? If we want to add them up, we're going to get a formula that looks like this. Right? We can approximate this volume by adding up the volume of a bunch of these guys. And if we turn that into an integral, the integral will look like that. If we integrate, so if we find a formula for the area at a given point along the axis, and we integrate that formula, that will give you the volume. That's the idea. And A and B are the places where we're starting calculating the volume and finishing calculating the volume. That's what that A and B represents. Any questions about this sort of visualization procedure, where this formula comes from, before I go on to show examples of using it? Okay. So, again, for this method to work, we need to have a formula for the area of a cross-section. Right? Again, when we're slicing it this way, we're taking cross-sections this way. We need to have a formula for what the area of each of these things is going to be. Here it's not going to be a problem because these slices are going to be rectangles, right? The area of a rectangle is an easy thing to calculate. If the slices were some weird shape, this would become a lot more difficult. And you won't see problems like that in this course. Future courses you might. Those sorts of things where the slices are weird shapes, you're going to need to use what's called a double integral. So if anyone goes on to take Calculus 3, you'll see those sorts of things. But anyways. Okay. So I'm going to do some examples here. Now I know visualizing these sort of things is difficult. So what I've got is I've got a link to, oh boy, update. Great. I'm sorry. I should have checked before. The Java version of the computer might be out of date. So I may need to update the Java on this thing. Let's just see if this works now. Yeah, no, it still tells me to download Java software. Install. Oh, great. Good, that should work now, hopefully. What? It's still telling me to go to close browser and continue, save your working data. Okay, now does it work? What? It's still telling me to.
Just try.
Okay, now it's working. Sorry, I thought it had installed already. Anyways, while this is installing, the visualization will have to wait. I'm going to sort of draw a picture of this. So here we're trying to find the volume of a pyramid which has height 2, and its base is a square of side length 2. Right? So the idea is what we need to do to calculate this area is we need to find a formula for the area of this rectangle, the area of a rectangular slice. So the idea, the first thing I'm going to do is on the pyramid, there's the pyramid, I'm going to measure, actually I'm going to measure a distance x up from the bottom. And I'm going to draw a square like that. Now the idea is, it turns out, on this big pyramid, this height is 2, this distance is 2. On this small pyramid is a miniature version of the big pyramid, which means the ratio, so here, this blue line and that blue line are the same, right? Those are the same line. Since the small pyramid is an image of the big pyramid, this green line and that green line are going to be the same length, right? Because this is a miniature version of the big one. This green line is 1 minus x, which is 2 minus x, sorry. The top is 2, the bottom is 0. So this one has also got to be 2 minus x. So this green square, the area is going to be 2 minus x squared. So that means the volume is going to be the integral. Now x starts at the bottom of the pyramid, that's x equals 2. It ends at the top of the pyramid, that's right, so x is 0 to x equals 2. So the bottom is x is 0, the top is x is 2. And here we're doing 2 minus x squared dx. Okay. Those, hopefully it works now. So, sorry, now the Java's loading and I can actually show you the visualization of it. Run. Okay. Oh, this is, no, never mind. Squares. Okay, so this is a visualization of this pyramid in question. So now here you can't actually see the pyramid. Here all you see is a cross-section of it. If I hit generate the solid, oh, there, sorry, right? There we go. There's the pyramid. Now they turned it on its side, so they draw the x-axis like this, right? This point in the pyramid is x equals 0. This point in the pyramid is x equals 2. Right, and what I'm doing when I'm calculating the volume of this thing is I'm taking a bunch of different cross-sections. So let me just get rid of the pyramid for a second. I'm taking a cross-section here, 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 a cross-section here. And I'm taking all those guys and I'm adding them all together. Right? And what I need to do is I need to find a formula for the area of one of these guys. I want to find the formula for the area, so I take this distance and square it, because this thing is a square. Right? So if I want to measure this distance, I'm going to take the distance between this line and this line. It turns out they found the equations for those two lines. This one is y equals 1 minus x equals 2. This is y equals negative 1 plus x equals 2. If you subtract them, you will get this same formula, 2 minus x, for the side length of that square. But yeah, this was sort of just a picture to help you visualize what's going on here. So, sorry, what was I? Oh yeah, so now I want to finish the example. So to finish the example, I've got to integrate this guy. So 2 minus x squared, if I expand it, becomes 4 minus 4x squared. So 4 minus 4x plus x squared. Integral of 4 is 4x. Integral of negative 4x is 2x squared. Integral of x squared is x cubed over 3. And this whole thing's got to go from 0 to 2. I plug in 2. 4 times, I'll get 4 times 2 minus 2 times 2 squared plus 2 cubed over 3 minus, and I plug in 0. I'll get 0 for all of these when I plug in 0, so I'm just going to write equals 0 here. If we calculate this is 8. 2 times 2 squared is 8. 2 cubed over 3 is 8/3. So the final area is just 8/3. The volume, sorry, final volume is just 8/3. And if you know the formula for volume of a pyramid, you can find it that way. It should give you the same answer. Any questions about example 1? Yes?
You get 2 minus x for both of those.
Oh, here this distance is x,
Yeah.
this distance is 2. So therefore this thing's 2 minus x. Right? And this little green pyramid is the same ratio as the big pyramid. Since this length and this height are the same, this green length and this green height are the same. Yeah. Yes?
Can we do it from other side?
Yes. So if you did it, here's another integral. If you measure x from the top going down, you would get this integral. And this will give you the same volume. So if you measure it from the top going down, I just want to mention this. That formula actually becomes a little bit easier. So if I make this distance x, right, the distance from the top there, then this distance, this black distance is the same as this black distance for the same reason as before, so this distance is x. So in that case, the area would just be x squared. And x starts at 0 at the top, goes to 2 at the bottom. That's where that comes from. They would give you the same answer. If you integrate that one, it's going to be slightly easier integral to give you the same answer. Yeah. Any other questions before we move to example 2? Okay. So example 2 is going to be a little bit more complicated. And one of the reasons example 2 is a little bit more complicated is here I haven't been told what the radius of this disk is. I've just been told we have a solid whose base is a circle of radius r. And if we take a cross-section parallel to the base, perpendicular to the base, sorry, so we take cross-sections like this, these guys are squares. So imagine you've got a circle down here, and if we take slices like this, those slices are all square-shaped. Here's another drawing of it. Here's a circle on the bottom. Cross-sections like this are all squares. So all those shapes are squares. Let's go circular base and a squares cross-section this way. So the key thing is that in order to come up with an integral for this, we need to create an axis. I'm going to put the axis here. The reason is because we're taking cross-sections this way, which means that we want to integrate that way, right? Your cross-sections, your slices should always be perpendicular to the way you're integrating. This point on the axis I'm going to call negative r, and this point I'm going to call r, which means the circle is centered at 0 on that axis. Now what we need a formula for, to get a formula for the area, is we need a formula for that side of the square. Right? How long is that side of the square going to be? Well, one way I can show that is using this picture. This is the side of the square we're going to do. What we know is we know this distance x. We want to calculate that distance there. Well, one way we can do it is using a right angle triangle. Right? This distance is x. This distance is r. So this distance here is going to be the square root of r squared minus x squared. So this whole distance, sorry. This diagram's not very good. Okay. Here's the circle. Here's 0. We've gone some distance x from 0. This distance is r. This is a right angle triangle, which means that side of the triangle is the square root of r squared minus x squared, which means this red line here is 2 times the square root of r squared minus x squared. So if we want to find the area, so we know that this distance is 2 times the square root of r squared minus x squared. So if we want to find the area of a square, it's going to be this side length squared. So what we've got to do for this thing is we've got to integrate, and we're going to start at negative r, we're going to end at r, right? That's where the x-coordinate goes from here to here. The area of one of these cross sections, the area of one of the squares is this guy. And we've got to integrate this. Now, if we square this thing, we've got to square the first guy and square the second guy. 2 squared is 4. R squared minus x squared squared is just r squared minus x squared. The 4 can come out as a constant. Now, when we integrate this guy, r here has no x's in it. R squared is just a number like 4 or 9 or 16. Right? It depends what r is, but it's still just a number. The integral of 4 would be 4x. The antiderivative of 4 would be 4x. The antiderivative of 9 would be 9x. So the antiderivative of r squared is going to be r squared x. When we do the antiderivative of x squared, that gives you x cubed over 3. And this whole thing, so we've got to go from negative r to r. And so then we just need to plug in and subtract. So if we plug in r, we'll have, the 4 out front is still going to be there. R squared x is going to become r cubed when we plug in r. X cubed over 3 will become r cubed over 3. That's what happens when you plug in r. When you plug in negative r, you'll get r squared times negative r, which is negative r cubed. Here you'll have negative r cubed over 3. Here r cubed minus r cubed over 3 is 2r cubed over 3. This negative will make those two things positive. That'll be another 2r cubed over 3, so we'll have 4r cubed over 3 inside here. That gives you 16r cubed over 3. That is the volume of this thing. And you'll notice the volume of this guy depends upon the radius, which should be expected because we're talking about something which has radius, different radius for each r. One thing to mention about this particular one with the r not being known is an example of a sort of a written assignment difficulty question rather than a test difficulty question. If I was going to give you something on the test, I would tell you, like, what is the side length of the base, or here, what is the radius? If I was going to give it to you on the test. Any questions about this example before we move to the next one? Okay. So, okay. So the last one, example 3. Here again, we want to follow the volume of the solid. In this one, the base is a triangular region with vertices at 0, 0, 1, 0, and 0, 1. Right, this is the point 0, 0, this is 1, 0, this is 0, 1. There we go. So that's the triangular region. If you take cross sections perpendicular to the y-axis, that's the y-axis there. If you're taking cross sections perpendicular to the y-axis, those cross sections are going to be equilateral triangles. So again, this is going to look like this triangle with something, a sort of triangular thing spiking out of the board towards you. Maybe it's like a tent, and this is the bottom of the tent, and you've got some poles sticking out the top of it. Anyway. Now, one thing to mention, I'm not going to expect you to be able to come up with a formula for the area of an equilateral triangle. I will tell you what the formula for the area of an equilateral triangle is. Right? The formula for the area of an equilateral triangle is square root 3 over 4b squared. So the area, actually, I'm going to say, is square root 3 over 4b squared. Now one thing to mention here, you notice I've written area as a function of y, rather than area as a function of x. And the reason here is here I'm saying this cross-section is perpendicular at 90 degrees to the y-axis. We're taking cross-sections like this, we're integrating along y. We're not integrating along x. We're taking slices like this. So now the question is, if I have a given y-coordinate, what's going to be the area of this triangle? Well, that distance there is my b, right? This black line here is y equals 1 minus x, right? It's got a y-intercept of 1 and a slope of negative 1. Now, if I want to, here, I want to subtract the x-coordinate of here minus the x-coordinate of 0. To get the x-coordinate of here, I'm going to have to rearrange this. Move the x to the other side, y to the other side, it becomes x is 1 minus y. So this x-coordinate is 1 minus y. This x-coordinate is 0. So if I want to measure this distance, I've got to take 1 minus y minus 0. So the b here is 1 minus y. So the area is going to be square root 3 over 4 times 1 minus y squared. So it's going to be square root 3 over 4. This 1 minus y squared gives you 1 minus 2y plus y squared. And that is what I'm going to have to integrate. So the volume is going to be here, the integral of the area. The integral is going to start, the lowest y-coordinate here is 0. It's going to stop at the highest y-coordinate, which is 1. The area is square root 3 over 4, 1 minus 2y plus y squared. Then that square root 3 over 4 is a number, so I can pull that out front of the integral. And then I should take the antiderivative of each of these guys. The antiderivative of 1 is just a y. The antiderivative of 2y is y squared. The antiderivative of y squared is y cubed over 3. This whole thing's got to go from 0 to 1.
Can you draw the solid you get?
Yes. I'm going to draw it over here. Thank you for asking for that. Looks something like that.
Okay.
Right? So this cross-section is an equilateral triangle. If you draw a cross-section here, it's also an equilateral triangle. If you draw a cross-section here, it's kind of a triangular pyramid. It's a sort of pyramid type shape. Triangle, but with a triangle base. This one's also an equilateral triangle. And this is the tippy top of the pyramid, and this is the base of the pyramid.
And the base is what we're looking on the x-y axis?
No, this is the back of this pyramid.
Oh,
Right, because we're taking cross-sections this way,
right.
which is cross-sections this way. Yes. Thank you for asking, though. Yeah. Okay. So sorry, to finish this off, I'm just going to take this thing, plug in 1, plug in 0, subtract. So it'll be square root 3 over 4. If I plug in 1, I have 1 minus 1 squared plus 1 over 3, which is 1/3. If I plug in 0, I have 0 minus 0 squared plus 0 over 3. Square root of 3 over 4 times 1/3 is square root of 3 over 12. That's the volume. Okay. Any questions about this example? So the key thing here is to be able to visualize what's going on a little bit and find a formula for the area of a cross-section. Once you have that formula for an area of a cross-section, all you need to do is integrate. Yes?
For this example, can we just say that the base is equal to y and pretend that it's been flipped?
Yes. So if you rotate this solid, you can rotate this solid 90 degrees or flip it or whatever and visualize it differently. As long as you sort of, if you're doing that on the test, make sure you write, I've rotated it 90 degrees or whatever. just to sort of symbolize that, yes, I have done some sort of rotation to it. If you want to do that, that is great. There's nothing wrong with that. You know, if you can visualize that sort of rotation. I like to do it this way because for me, like, it's easier for me to integrate with respect to y than it is to rotate the whole thing. But if you're someone who prefers to rotate the whole thing so you can integrate with respect to x, that's also totally fine. Any other questions about these guys? Okay. So, the next thing I'm going to talk about are these things that are called solids of revolution, which is a very specific sort of type of three-dimensional solids that we can calculate volumes of using slicing. These turn out to be usually some of the easier ones to do volumes of using slicing. These ones become a little bit more difficult for people because these ones don't have, there's no one systematic method which works for all of these problems, whereas the solids of revolution do have sort of one systematic method. I just want to mention that in this course you do need to know how to do both of them. A lot of people sort of practice the solids of revolution and just don't bother practicing these ones. That's why I covered these ones first. But the solids of revolution ones should be a little bit easier for people to get through. So one type of solid that we can easily find the volume of via slicing are those which can be formed by revolving a region of the xy plane about either the x-axis or the y-axis. What I mean when I'm talking about this is a picture like this one here. That's loading, and once it's loaded, I can sort of show you what's going on. Run. Okay, so here we have a region in the xy plane. This is the region between the graph of this function and this function, x equals 0, x equals 1. Now what we can do with that region is we can revolve it around the x-axis, and we do that, we create a solid. So we take this thing, we rotate it around the x-axis, we get a solid. That's the idea. And so the idea is if we want to calculate the volume of this guy, what we're going to do is we're going to start with a little rectangle, that red rectangle there, and we're going to turn that red rectangle into a slice of the solid. How do we turn the rectangle into a slice? Do the same thing we do to the region, revolve it. So the idea is when you've got a solid of revolution, the slices of that solid of revolution are going to look like discs, oftentimes. They're going to look like circles. And if you rotate the whole thing, that slice will look like that guy there. And we'll have a bunch of different slices, one here, 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 etc. Oh, show in slices. There we go. So there's a bunch of different slices, right? And all those slices have been formed by taking these rectangles and rotating them around. So again, we started with like, you approximate with these guys, with these rectangles, rotate the rectangles around. That gives you the solid of revolution. That gives you the slices. So the idea is the cross sections of a solid revolution are oftentimes just circles. Right, those cross sections I drew were just circles. If they are just circles, the area is just pi r squared. Right? The area of a circle is pi r squared. Now oftentimes, like in that previous example, the radius of the circle was just the distance from the x-axis to the graph. So in that case, the radius of the circle is just the y-coordinate of the function. The radius of the circle is just f of x. And so in that sort of situation, the volume is going to be the integral of pi times f of x squared dx. Right? The area is just pi times the radius squared, and the radius here is f of x. Now one thing that happens some of the time is that rather than having circles, sometimes we have slices which are what are called washers, or annuluses. So here, if we take that little red rectangle there, and we rotate it, let me see if I can, there we go. If we rotate that little rectangle there, you'll see that this slice is not a circle, but it's like sort of donut-shaped, or washer-shaped. I don't like to say donut-shaped because donut implies it's sort of round. This looks more like a washer. And if we revolve the whole thing, if we look at it, we see it's got this hole in the center. And that's because these guys aren't circles, but they're washers. So one thing we will also need to do, some of these guys, is the formula for the area of a washer. And this is the formula for the area of a washer. It's pi times the outer radius squared minus pi times the inner radius squared. So I just want to mention, you need the formula for an area of a circle, you need the formula for an area of a washer. The one for the area of the washer I will usually give you on the formula sheet on your test. So you don't have to worry too much about memorizing that. Area of a circle you should know by now. Anyways, so I'm going to do a couple examples using this. So again, when we're finding the volume of a solid of revolution, what we do is we first sketch the region in question, visualize rotating the region about one of the axes, draw a little rectangle that sort of approximates a slice of this thing, rotate that rectangle around the axis so we can see what shape we're dealing with, find a formula for the area, integrate the formula for the area. So the first example of this, example 4, we have a solid which can be obtained by rotating the region between the curves y equals square root 25 minus x squared. Y equals square root 25 minus x squared. That turns out to be a semicircle. Again, you could find this easily with your graphing calculator. Y equals 0 is that line there. X equals 2 is going to be here. X equals 4 is going to be there. So the region we're talking about is this green region. And we're rotating the region about the x-axis. Right? So if we rotate it about the x-axis, we will get something that looks like that. It looks sort of like a slice of a ball. So if we take this green thing, spin it like this around the x-axis, we will get this sort of slice of a sphere shape. Here, let me do it in black so that we'll realize that green may be invisible to a bunch of people. So here's this end of it. Here's this end of it. It looks like that. Again, I don't know if that really helps that much. Again, if we rotate the whole curve, we get a ball. We're just taking the part of it between x equals 2 and x equals 4. So it's a slice of a ball. So if we want to measure its volume, what we've got to do is find a formula for the cross-sectional area. We're going to take a slice like this red rectangle here. We're taking slices this way. Because if we take this slice and we rotate it about the axis, you'll get that red shape. That red shape turns out to be a circle. What's the radius of that circle going to be? The radius is going to be that distance r there. So the radius of that circle turns out to be the y-coordinate of this curve. So then, the area is going to be pi times this radius squared. If we square this thing, it gets rid of a square root. So the area is going to be pi times 25 minus x squared. So if we want to find the volume, we've just got to integrate this area. Now, where does the integral start? Where does the integral stop? This region is between x equals 2 and x equals 4. So we're going to start at x equals 2. We're going to end at x equals 4. We're going to integrate pi times 25 minus x squared with respect to x. So I'm going to pull a pi out front. Take the antiderivative of 25. That's 25x. Antiderivative of x squared is x cubed over 3. This whole thing goes from 2 to 4. Plug in 4. 25 times 4 is 100. 4 cubed over 3 is 64 over 3. Plug in 2. We will have 50. 2 cubed is 8. I'm just going to leave it like that. Again, we could simplify this if we wanted to, but for a lot of purposes. Here we have a number. It's a complicated number, but it is a number, and we could evaluate it. Any questions about how I did this example? Okay. Now, one thing to mention is in some situations, in some examples, we're going to have to do the same thing we did when we were working with areas, which is we have to find points of intersection before we can actually figure out what our limits of integration are. So here's example 5. Here we want to find the area between the curves 1/4 x squared, which looks like this. So that curve there. And 5 minus x squared, which looks like that red curve there. And the idea is, again, we're rotating this thing about the x-axis. So we're rotating it that way. So the region we're talking about is that green region there. And if we rotate it about the axis, oh boy, I can't figure out how to draw it. It's going to look sort of like a ball with 2 holes punched in the end, a hole punched in here and a hole punched in there. Sort of what it's going to look like. So when we're integrating this, we're going to be taking strips like this, right, blue strips like this, and our limits of integration are going to be where this region starts and ends. So to find where the region starts and ends, we need to find the points of intersection, which means we need to set these two guys equal to each other and solve. Let's multiply both sides by 4 to get rid of the 1/4. This will be 20 minus 4x squared equals x squared. Move the 4x squared to the other side. 20 equals 5x squared. Subtract 5, sorry, divide both sides by 5. 4 equals x squared. So x is plus or minus 2. So that's the first thing to mention. We now know what those limits of integration are. This one's at -2. This one's at +2. The other thing we need to visualize is, what do those slices look like? Well, if we take this thing and we rotate it, we get this blue thing, which is a washer. The outer radius of the washer is the distance from the middle to the edge. That's going to be the y-coordinate of this curve. The inner radius of the washer is this little distance up here. That's going to be the inner curve. So the area is pi times the outer curve squared minus pi times the inner curve squared. So the volume is going to be the integral from -2 to 2 of this area. Pi times 5 minus x squared minus pi times 1/4 x squared dx. And this is an example of a question where if it was on the test, I only asked you to go this far. I wouldn't ask you to actually complete the integral. You can do it. There shouldn't be any problems if you did sort of want to expand these two guys, simplify as much as you can, complete doing the integral. It just takes some extra time. But yeah, you don't need to do it every time. So this is an example of a question. I just say find, write out an integral for the volume. So write out this thing, and then you can get your computer or whatever to do this for you at home. Like this, yeah. Any questions about example 5? Okay. So I've got 2 more examples for you before the break. And those examples, the last 2 are going to be situations where you're going to be rotating about the y-axis. Here so far, I'm always going to be rotating solids about the x-axis, which is one of the reasons I always cut my solids like this. Because if you slice them like this and you rotate the slice about the x-axis, you'll get either a circle or you'll get one of these washer shapes. However, if we're rotating this way, we want to slice it this direction rather than this direction. So if we're rotating about the y-axis, we're going to need to take horizontal slices. And when we're doing horizontal slices, when we're measuring those radiuses, we're measuring horizontal distances. To measure horizontal distances, you need to have an x-coordinate as a function of the y-coordinate, rather than y as a function of x. So example 6 is an example where I'm doing this. Where's my black marker? There's all 4. So example 6. We have the function y equals ln x. We have y equals 1. We have y equals 2. Sorry, though. And we have x equals 0. X equals 0 is this line here. So the region we're talking about is this green region here. And we're rotating that green region about the y-axis. So we're going to get a shape that looks like that. Sort of looks like a cork. It's wider at the top than it is at the bottom, and it's round. So if we want to find the volume of this, we're going to find a formula for the area of a cross-section. We're going to take cross-sections like this red one here. When we rotate that, that's a circle. What's the radius of this circle going to be? Well, the radius of this circle is going to be the difference between these x coordinates. Now here we have y as a function of x. To get the x coordinate this time, I'm going to have to solve this for x as a function of y. We take y equals ln x, but ln on one side is the same thing as an e on the other. So we can really think of this thing as x equals e to the y. So this part of the radius is at e to the y. This is at 0. Right? This is just the x coordinate. This horizontal is just the x coordinate, e to the y. So the radius here is just e to the y. The area, and again, this is the area as a function of y because we're integrating with respect to y. We're taking slices this way. The area is going to be pi times e to the y squared. So the volume is going to be the integral. Y is going to start at 1. It's going to end at 2. Right? This is the lowest y coordinate. It's the highest y coordinate. We're going to have pi times e to the y squared dy. Now, if we simplify, well, firstly, we can pull pi out front. E to the y squared can also be written as e to the 2y dy. And if we want to integrate e to the 2y, we're going to need substitution to do it. Because here we have an inside function. We have a 2y rather than just a y. So the substitution we're going to use is u equals 2y. So du is going to be 2 dy. Right? The derivative of 2y is just 2. When y is 1, u is 2. Right? So at this lower limit, the u is going to be 2. When y is 2, u is 4. This is just 2 times 2 is 4. This integral will become pi times the integral from 2 to 4 e to the u. Oh, sorry. I forgot to say if du is 2 dy, that means dy is du over 2. So it's e to the u times du over 2. I can pull a 1/2 out front. So I'll have a pi over 2 out front, integral 2 to 4 e to the u du. If we take the antiderivative of e to the u, it's just going to be e to the u. It's going to be e to the u from 2 to 4. So it's going to be pi over 2 times e to the 4 minus e to the 2. And that's the formula for the volume. Any questions about example 6 here? Yes?
Would there be any times when it would revolve around the same axis but at a different x point, like at x equals -2 instead of 0?
That's 6.2.3 that I've cut. I'm not teaching that this course just because I know it causes students difficulties. I don't want to spend too much time on this particular section. I don't feel that volumes are the most useful of the applications that we cover, which is one of the reasons I don't want to spend too much time on it. I want to spend more time on the ones that are actually more useful. I mean, this is nice because it's purely mathematical. You don't require any knowledge from any other fields. But I want to spend more time on the ones that you'll use in physics, on the ones that you can use in like economics, on the ones that you can use in biology. Like, I want to spend more time on those applications than these ones. Yes?
So, this method, I call it is this method, right?
This is called the disk method. Yes.
Yep. Will you teach the shell method?
No, I'm not covering that this course.
Okay.
Yeah. And the reason is because, again, I don't think the volumes are the most useful application. I know very few people who've actually used this stuff after Calculus 2. Except maybe people who are math people who go on to specifically study like differential geometry and those sorts of things. People who specifically study how to calculate volumes and stuff like that. In that sort of case, then yes, this is important. But most people are not going to use this after this course, and so I'm going to spend more time on the other applications. Yeah. Okay. So last example before the break, which is example 7 here. Here, I just ask you to set up an integral for this volume rather than actually evaluating it. And the reason for this is because it's a situation in which the integral is going to be complicated enough that you're not going to really be able to do it yourself at this point. We won't have the methods necessary to do it yet. Actually, no, never mind. You probably can. It'll just be messy now that I think about it. So here's the graph of y equals x squared. Here is the graph of x squared plus y squared equals 1. So you'll notice here that x squared plus y squared equals 1 is not something you can graph with your graphing calculator. So if this sort of question was going to come up on the test, I would give you this picture to start off with. The other thing to mention, oh shoot, I should have gone about finding intersection points for you. So the region we're talking about is the region for y bigger than or equal to 0. So it's this part, this red part. And we're rotating the red part about the y-axis. So the idea here is if we take a slice like this, if we take a slice there, we get that green sort of disk. Now if we take a slice here, we get this blue disk. And the thing to note, the thing that's really annoying about this problem is the radius of the blue disk and the radius of the green disk are different. The radius of the green disk comes from this curve. The radius of the blue disk comes from this curve. So the first thing I'm going to do is I'm going to find the intersection points. And the way I can find the intersection points is take y equals x squared, plug it into here. I will get x squared plus x squared squared equals 1, x squared plus x to the 4th equals 1. So x to the 4th plus x squared minus 1 is 0. Now to solve this, now the other thing I was going to mention about this particular problem, I should have done this ahead of time. I should have written them on the slide so I'd actually know what they were. Finding the intersection points requires doing the quadratic formula and then doing an extra square root. It's really annoying. And I wouldn't, again, it's something else I would not ask you to do on your own. So here, this is a quadratic formula in x squared. So we use the quadratic formula to figure out what x squared is, which is negative b. b is 1, plus or minus the square root of b squared, which is 1, minus 4 times 1 times negative 1, all over 2 times 1, negative 1 plus or minus, this is square root of 5 over 2. So this is the, what x squared is. Now the question is it going to be negative 1 plus this or negative 1 minus this? Well, x squared has to be positive, so therefore it has to be negative 1 plus. We can get rid of this minus situation because x squared has to be positive. X is going to be plus or minus the square root of this. Now, if we want to find the coordinates of these points, so this one is positive, the square root of that thing, negative 1 plus the square root of 5 over 2. The y-coordinate here is just this thing squared, because y equals x squared. So the y-coordinate is just negative 1 plus square root 5 over 2. And this guy is going to be the same but negative. It's going to be negative the square root of negative 1 plus square root 5 over 2, comma negative 1 plus square root 5 over 2. Right, it's the same as this guy, but the x-coordinate is negative. The y-coordinate is the same. So, to mention, when we're calculating the radius of these guys, the radius of this guy and the radius of this guy are both x-coordinates. Right? So to get the radiuses, we're going to need to take this thing and solve it for x. So here x is going to be plus or minus the square root of y. For the green guy, we can rearrange this. X squared equals 1 minus y squared. So x is plus or minus the square root of 1 minus y squared. So the idea here is we're going to calculate the volume in two different pieces. We're first going to do the green piece. Right, so we're integrating with respect to y. We're integrating this way. We're taking slices like this. The piece with the green slices, the y-coordinate goes from 0 to this thing. The area is a circle, so it's going to be pi times the radius. The radius is going to be the x-coordinate of this guy. Now, whether it's plus or whether it's minus is actually not going to change because it's r squared. So r squared is going to be 1 minus y squared. I'm actually going to write this down here. R squared is 1 minus y squared. This x is the radius. We square the radius, we get this. Dy. So that's the first part of the integral. Plus, and then the blue part is going to go from here up to the top of this thing. The top of this thing happens at y equals 1. So negative 1 plus square root of 5 over 2 up to 1 pi times, now here this is the x-coordinate. Here the x-coordinate is basically plus or minus the square root of y. Here the radius squared is just going to be y. And this will give you the total volume. This will give you the volume of the part below this line. The blue will give the volume of the part above this line. And the reason I'm not asking you to evaluate this is actually not because these functions are difficult to evaluate. Because of these really annoying numbers here, the negative 1 plus square root of 5 over 2. Don't want you to have to plug that into anything. So that's the real reason I'm not asking you to evaluate it. And again, one thing to mention, if I was giving this to you on a test, I would have told you the coordinates of these points already. So that you'd have a picture like this. These points would already have the coordinates labeled if I was going to give this to you on a test. Any questions about example 7? Okay, so take a 10-minute break, so come back at 12:48. Again, likely, due to the way time's working out, I'm probably not going to cover 6.2.4 either. I'm going to do 6.5 right after the break. If for whatever reason 6.5 goes faster than expected, I will come back and cover this quickly. If 6.5 goes same speed as expected, 6.2.4 is not going to be covered. Anyways, yeah, so take 10 minutes.